Welcome back. Nature in Code Chapter 4. We just went on a short mathematical excursion and we established that two forces are acting on genetic variation in our current world. That is the force of genetic drift, which acts to decrease the genetic variation. And we've established that in many videos before in Chapter 3. And now we have this term here that tells us something about the increase in genetic variation due to mutation. And we have recently, in the earlier videos of this chapter, developed some code with DNA sequences, toy DNA sequences, to just demonstrate briefly just how quickly that genetic variation gets created. So now what I would like to do is I would like to go back to our original model where we have two alleles at a specific location in the genome, and we're trying to understand the dynamics of these two alleles. So we've previously established that if you start with an A1 allele at 50% and an A2 allele at 50%, then you'll see these interesting genetic drift dynamics that we plotted in the browser. Now, I would like to change this just slightly, and I would like to assume that in the beginning, our population is exclusively A2. And so at this point, we now introduce a mutation of the A1 allele. So A2 mutates, becomes A1, and now it exists in a single copy. And the question is, what is the fate of that mutation? So in some sense, we can plot this as follows, or sort of explain it as follows. This is our P, right, which is still the frequency of A1. And we start here at a very low frequency, because here what just happened is that there was no A1, it was all A2, but then a mutation happened that introduced A1 into the population. Now the trick of course is that here at this point, P is exactly 1 over 2n. So then of course this is time here. Because in our population of n individuals, we have 2n alleles. They're all A1, except this one copy that is, they're all A2, except this one copy that is A1. So its frequency is 1 over 2n. It's very rare. And if you think about it, that happens with every allele. Every allele that you see in the world today, it doesn't matter how common, even the most common alleles that you can possibly find, had at one point to start as a single copy. And that is really quite remarkable. Now, keep in mind that in our world at the moment, we still don't have any selection. So all alleles are selectively neutral, and that simply means that no allele is in any way better or worse than the other. They're equal when it comes to, affecting survivability or fitness or anything like that. They're just equal. They're selectively neutral. So granted, many of the alleles that you see in populations today didn't start out necessarily as neutral alleles. They started out as beneficial alleles, and that made their rise to dominance a little easier. But still, there are many alleles that started probably as neutral alleles. And the question is, what is the fate of such a neutral allele? And you can imagine that, oftentimes the fate is that it immediately goes to extinction again. Other times, it could perhaps, stick around for a while, even make some copies of itself, and then go to extinction. But there are also situations that you can imagine where it sticks around for a while, and then, just by pure chance, because remember, drift is essentially chance, it goes to fixation. This can happen. So the question I want to answer now is, what is the probability that this happens? What is the probability the probability of fixation of a neutral allele. Well, and here's the result. I'm going to show you the result right away, but then we're going to implement this in code to verify this. Turns out the answer is very simple. The probability of fixation of a neutral allele is its frequency. That's it. You might recall back in the day when we created these genetic drift simulations where we started at p equals 0.5. You may have remembered or may have sort of observed that about half of the simulations will be such that A1 will go to fixation, and about half run in the way that P will eventually go to 0, so the A1 allele will be lost. And that's, of course, completely in line with this observation. Now, what this means here is that if we run simulations where we introduce the A1 allele at this frequency, which means there's just one copy of it in the beginning, in 1/2n of all simulation runs, it should go to fixation. So say, in an example where n is 100, then P will be at the beginning 1/200, which will be 0.005. And so that is the probability that this allele will go to fixation. And you can, of course, see that the larger the population, the smaller this probability becomes, which makes intuitive sense. So I want to implement this idea now in code using code that we've written before. Now, I'm not going to copy this code. I'm just going to start from scratch, but it's simple code, so we should be able to do this right away. So open an empty document and create your template here. Doc type HTML. Again, I'm going to start with my HTML tag. Oops, should be a slash. And then I have my head and my body. Oops, body. Okay. And again, oops, I am going to add my code here. So the script tag, I'm going to add it here. Okay, so let's get started. Well, the first thing that we need is we need to create this next generation function that creates the genetic drift dynamics, and we used to implement this with a function called next generation, and I'm going to do this here as well. Next generation. Actually, let me just go ahead and save this document so that I get the syntax coloring. So I'm going to call this probability fixation.html. All right, there we go. Okay, so we had our variable that defined how many draws we would have, and that was 2 times n. And of course, that would also mean that I would have some global variable here somewhere that actually defines n. And I'm going to set this to 100, so that's the population size. And then I would have 2 counters, one for the A1 allele, one for the A2 allele, which I'm going to call, A1 and A2. And then I would have this loop where I would say, well, okay, for however many times I need to do this, and this is of course draws, and increment I by 1. I am going to flip a coin, or rather, more precisely, call math random, and then if that is smaller or equal to the current frequency of the A1 allele, then that means we picked an A1, and I'm going to increment this counter by 1. Otherwise, we picked an A2, and I'm going to increment this A2 counter here. And then, oops, +1. And then once I've done this, once the for loop has finished its course, the new P is going to be however many A1 alleles that I have divided by however many alleles I have in the population. And what we should do, of course, here is to define this variable P. Now, in the previous simulations, we did something like this. P equals 0.5. This was our starting value. Now we're going to change that in a minute, because what we want to do is we want to start P not at 0.5 but at 1 over 2n. So this is the function now that just creates this new P in each generation, calculates this new P, and then we will, if you could plot these P values, and you will get these drift simulation plots that we had before. Now what I would like to do is I would like to run simulations, but I wouldn't. So last time what we did is we ran a simulation and we ran it for 100 generations, 200 generations, 1,000 generations, what have you. Now in this particular case, I'm not interested to run a simulation for a specific predefined number of generations. I just want to run it for as long as there are still both alleles in the population. As soon as one of them has gone to fixation, I'll stop the simulation run. And now if I can do this repeatedly, I can just basically observe how many of those times did the A1 actually go to fixation as opposed to the A2. So let's set up a variable here that defines how many simulations we're going to run. And let's set this at 10,000. So we're going to run a lot of simulations. We're not going to plot 10,000 simulations. And you might want to choose a smaller value at the beginning if you feel like your browser may not be able to handle this in terms of speed. I'm pretty sure mine does, but you might want to start with 100 or 1,000. And then I'm going to basically run a loop here. So for var I, and I want to do something simulations many times. So I smaller than simulations. And of course, I equals I plus 1. Okay, so here I want to call a function that triggers the simulation that runs until P has gone either to 0 or 1, which means that one of the two alleles has gone to fixation. So I'm just going to call a function that I'll have to define in a second. I'm going to call this run until fixation. Okay, so let us implement this function here, run until fixation. Function run until fixation. So what should this function do? Well, basically, it should begin at a set p-value, which I'm going to now set at 1 over 2n. Okay, whenever n, this should be an n. Whenever I start a new simulation like this, I need to reset my p to 1 over 2n. So that means I have one copy of the A1 allele. And that also means I can basically go ahead and just get rid of this initialization here. I don't need that value. I'm just going to say var p so that it's defined. Okay. And notice that I don't say var here, because that would mean the local variable, and that wouldn't be the same p as the global variable that we use here, and that's defined up here. So be sure not to use the var keyword here, because we want to use the global variable. Okay, so now I want to say, well, run this simulation, which means execute the next generation function here for as long as you need to. And what does that mean? Well, call this function for as long as none of the alleles has gone to fixation. And an allele has gone to fixation when P is either 0, which means the A2 has gone to fixation, or when P is 1, which means the A1 allele has gone to fixation. So I can use this new construct that we learned just a few videos ago, which was do while. So do. Now what should you do? Well, call this function next generation while a certain condition is true. And what is that condition? Well, again, the condition should be that P is not 0 and it is not 1. It is something in between. So one way to do this is as follows. You can say, well, as long as P is larger than 0 and P is smaller than 1. So here I'm introducing a new operator. This is a logical operator. It's a double ampersand, and it means and in logical conditions. So if you have multiple conditions, you want to say, well, I want to do something if this condition is true and this condition is true, then you use this terminology. There's also the logical or, which you would write like this. So this would say if P is larger than 0 or P is smaller than 1. But here in this case, you want the and. Both of those need to be true. And if both of those are still true, then it means both alleles are still in the population. Okay, so this will now call this function for as long as both alleles are still in the population. And I just noticed this here that I put this while here at the wrong location. I apologize. This should be up here because this belongs to the do. Okay, do while. Okay. Now, there's one piece that's missing. We now know that this generation or this simulation will run for as long as both alleles are in the population, and as soon as one of them has gone extinct, or as soon as one of them has gone to fixation, which is the same thing, it'll stop. The problem is we don't know which one. So, but we want to keep track of which one actually has gone to fixation because we care about how often the A1 allele goes to fixation. So the A1 will have gone to fixation if P equals 1. And so if that is the case after this loop here has finished executing, then we want to somehow keep track of that. So what we're going to do is we're going to generate a new global variable up here that keeps track. So I'm going to call this fixation, fixations of the mutant. Okay, fixations of mutant. That's just a counter. And so if P equals 1 down here, I'm going to increase this value by 1. And so now at the end here, after I've ran all these simulations, this fixations of mutant tells me the number of times the simulation has has ended in a way that A1 has gone from 1 over 2n to 1. That's exactly what I want. So we can now here simply print into the console fixations of mutant. That would tell us how many of those simulations have led to the fixation of the A1 allele. And I'm just going to divide that by the number of simulations so that I'll get the fraction. And now if we've done everything right, this should be 1 over 2n. This should be 0.005 as we've established on the slides previously. So let me save this, go to the browser, and open this document. File, open file, chapter 4, probability of fixation. Okay, I'm going to open this. not going to see anything here because I'm not really plotting anything, but I can go to the JavaScript console and wow, indeed, this is exactly 0.005. That's probably a little bit of a coincidence because there should be still some stochasticity in there. So I'm going to reload this. Yeah, now you see 47, so 0.0047, 0.0049, 0.0059. So there's a little bit of stochasticity because remember, after all, we're running stochastic simulations. But it looks like this is still fairly fast, so I'm actually going to up this by another factor of 10. Var simulations equals 100,000, and I'm going to run this, and now this will take a little longer here. But let's see what this gives us. 0.0049. So again, there's still some stochastic effect here, but this is now pretty close. So it is true. A neutral allele will go to fixation with the probability 1 over 2n if there's only one copy of it. And you can of course now play with these values. If you do play with n or p, be sure to adjust the number of simulations here. I felt confident to have a large number because I know, and you can deduce this easily too, that most of these simulations will actually be very short, right? Because you introduce the mutant allele and it will instantly go to fixation and then the simulation ends, okay? However, if you say here p equals 0.1, for example, rather than 1 over 2n, now most simulations will still lead to the extinction of this p allele, 90% in fact, as we now know. But this will take a little longer. So if you save this and you check whether your observation is correct, this should now lead to 10% of all simulations having the A1 going to fixation. So let's reload this. Now this will take a little longer, but it's still true, 0.1. Vice versa, you could, for example, say, well, I'm going to initialize this at 0.2. Save, reload. It's going to take a little longer still because simulations will take longer. But again, we're at 0.2 now, 0.21 because of the stochastic effect. So that's it for this video. We've just established and demonstrated with these stochastic simulations that the probability of fixation for a neutral allele is its frequency. And at the beginning, when the neutral allele is just a new mutant, it exists at frequency 1 over 2n, and correspondingly, that's the probability that this neutral allele will go to fixation. In the next video, we'll modify this code to understand, well, if it goes to fixation, how long is that going to take? So see you in the next video.